welcome to Calc 3. Today we are going to introduce vectors. Vectors and the operations that we're going to use to work with them are actually going to form the foundation for a lot of what we do in this particular class. So this is a really important video. So we're going to open with the definition of a vector. A lot of you are probably already pretty familiar with this from like maybe a physics or even like a business or an economics class. But a vector is really just a quantity that has the notion of both, it measures direction and magnitude. So just maybe like a quick real world example pops up in a lot of places is velocity. So velocity pairs speed with a particular direction. So your speed would be, for example, 50 miles per hour, and say you're headed east. This is a vector because your magnitude is given by the 50 miles per hour. And then the direction is provided by east. Now, an example that is maybe a little bit more mathematical and is actually going to form maybe a basis for working with vectors for other parts of the semester is the idea of defining a vector using 2 points. So what we can do is we can start at a point P and connect it to a point Q. And that will give us a vector. So starting at P and moving toward Q, like so. Well, there's a length there, that's our magnitude, and we had to move in the direction of Q, so that gives us our vector that we call PQ, and we denote with a little arrow on top. Now, since we're moving from P to Q, the order in which we're going is really important, and so we have these terms, the initial points for where we start at, and our terminal point for where we end at. And this isn't really the only way that we can work with vectors. There's another really common way that we're going to look at here. So this kind of reaches back into the idea of working with the Cartesian coordinate plane that we all know and love. So this is called the component form. And this goes to the idea of using coordinates. And the bottom line is that every vector can be broken down into 2 pieces, or however many dimensions it is that you're working with, which we'll talk about a little bit more later. So if we have this standard coordinate plane here, and we want to draw a vector v on it, like so, what we can do is we can say, okay, this vector reaches out this direction, but it has an x direction, and it also has a y direction. And sometimes it's really useful to be able to say that we want to express that vector v in terms of its x direction and its y direction. So this is its coordinate form. We take x and y and we put it in those angled braces like that. And this angled braces means that we're working with an entire vector. And I do want to highlight that you shouldn't really confuse this with a point, though it does reach out to that point x, y. When we have the angled braces, we're talking about the whole vector. And also, whenever we have angled braces, that means we're normally going to start at the origin. So here's a concrete example of this. I'll draw my coordinate plane here and put a vector on it. All right, so suppose that we have the vector v equal to 2, 3. So what this is going to look like, that 2 means that we go 2 to the right, and then the 3 means that we're going to go up 3 units. So this is our vector v equal to 2, 3, starting at the origin there. If we wanted to do another example, we can have our vector w, a little arrow, say like 3, -1, for example. That 3 means that we go 3 to the right, and then the -1 means that it's going to go down 1 unit, and then our vector looks like that. Now it may be useful to be able to move back and forth or between using points and using the component form of a vector to be able to express it. So I'm going to show how to go from 2 points to define a vector to being able to use the coordinate form or the component form. So given 2 points, say p equal to, I'm going to denote its x component with px and the y component with py. And another point, q equal to qx, qy, we can compute the component form of the corresponding vector using this formula. We're going to say that the vector PQ is equal to, and then we're going to use angled braces so that way we denote that we're getting ready to use a component form. And all we do is just find the difference between their coordinates, starting with our second point. That should be a P. There we go. All right. So for example, we're going to find the component form of PQ when P is equal to the point 2, 1, and Q is equal to the point 1, 3. All right, so using our formula, we're going to take the x component from Q, subtract off the x component from P, and do the same idea with the y components. And we're going to get, this is going to become 1 minus 2, comma 3 minus 1. So then that vector PQ is the same in the component form as 1, 2, or -1, 2, excuse me. And we can graph this and kind of see what the relationship is visually between these two. So here is our coordinate plane. -1 there. All right, so the point P was at 2, 1, right there, and our point Q was at 1, 3. So our arrow, or our vector, PQ, is like so. All right, but when we want to look at the component form, we've got to go -1 from the origin and then up 2, like so. Now, this vector is the same as this vector, but the only difference is that we just moved it down toward the origin. So one way to think about the component form is kind of stripping away any information about where it's located on the coordinate plane and just moving it to the origin. Now, what else can we do with vectors? Well, there's a lot of operations that we can apply, and the three that we're going to talk about today are going to be addition, subtraction, and scalar multiplication. And we're going to start with doing this in component form. So if we have two vectors, v, which I can write using its components, say vx, v sub y, and then similarly another vector w, which is w sub x, w sub y, when written in component form. If we want to add or subtract these two vectors, all we do is just do the same thing with their components. So v plus or minus w is going to be equal to vx plus or minus wx, and then vy plus or minus wy. So it's pretty straightforward. Just to give you an example, we can let v be equal to -2, 3, and w be equal to 3, -1. So v plus w then, we just look at its components, we're going to have that -2 plus the 3 from w, and then the y component, we're going to have 3 plus that -1, which is just equal to 1, 2. We can also take v minus w, which is equal to -2 from v minus that 3 from w, and then we have the 3 from v minus that -1 from w, which is just equal to -5, 4. Another operation we can do is multiply a vector by a scalar. And a scalar, if you're not familiar with the term, it's just a fancy way to say any old number. Okay, so if we have a vector v written in component form, and we want to take some scalar, which this right here means that this number a is in the real numbers, so we're just taking any number, then multiplying that vector v by a is the same thing as taking a and multiplying it by each of the components in v. So same idea as with the addition and subtraction, everything is just done in terms of by each component. And I have an example for working with the scalar multiplication as well. Let's suppose v is equal to 1, -3, and I'm going to do two examples in this case. So we're going to find, first of all, 2 times v, and then we're going to find -1 times v. All right. So in case A, 2 times v, all we do is take the 2 and multiply it by each of the components in v. So 2 times 1 and then 2 times -3. So then 2 times v is just going to be equal to 2, -6. In our second example, -1v, we're going to take that -1, multiply it by both components, and we're going to get -1, 3. Now I want to offer a little bit of maybe like a geometric interpretation of this as well. So I'm going to show you what it looks like to graph vector operations. So I'm going to start with this scalar multiplication example here. So if I have a vector v equal to 1, -3, and I want to find 2v and negative 1v on my graph. Well, what I'm going to start with is the coordinate plane, first of all. Run out of room there a little bit. Okay, so I like to start by graphing the original vector v. So that's just going to go right here, that 1, negative 3, and it's going to look something kind of like that. I'll put it in a dashed line, like so. So that's v. Now this 2v, we said earlier, was 2, negative 6. So that means that it's going to go right here, 2 down to that negative 6. And it's going to look something a little bit more like that, and it's going to kind of overwrite v a little bit because it just goes through v and then it continues onward and becomes just that vector stretched by a factor of 2. Okay, so really when you're doing a scalar multiplication, all you're doing is stretching the vector. All right, so in the case of negative v, however, this became negative 1, 3 now instead of 1, negative 3. So really what we're going to wind up doing is flipping this vector over, because now instead of going this way, we're going to go to the left, so we're going to have negative 1, and instead of going down, we're going to go up 3. So negative v is going to reach up to there. So all we did was take this vector v and then flip it over the origin, like so. So that's a really important interpretation of working with the negative of a vector, is that it's just flipping the direction of that vector. And something else that I want to take a quick moment to point out is that if we have a vector that is a scale multiple of another one, then we say that those two vectors are parallel. So two vectors, v and w, are parallel if the vector v is equal to some scalar a times that vector w. So for example, the vectors 1, 2, and that 2, or excuse me, 3 negative, oh my goodness, 3, 6 are parallel. Now this idea with scalar multiplication and working with this negative here is going to come into play when we do our addition or when we do our subtraction in particular. So now I'm going to show you just a graphing interpretation of addition and subtraction. So we're going to go back to those same vectors that we used before. Oops. That should be v. This guy is w. And we want to find v plus w. Here is our coordinate plane. Okay, so the very first thing we want to do is draw v. So v is going to be negative 2 and then up 3 like so. And then in order to add w to v using this graph, what we do is simply take v and then graph it starting at the end of, or excuse me, take w and graph it at the start, at the end of v. So we're going to take the tail of v, we're going to place it right there, and from there we're going to count out 1, 2, 3 units, and then go down 1 unit for that negative 1. So w winds up being right here, like so. So what we've done here is we've drawn the tail of W at the end of our vector V, okay? And then to get V plus W, all we do is connect the tail of V to the end of W. So this vector right here is your V plus W. And notice that this has the coordinates 1, 2, which is the same as we got earlier when we were doing this just in terms of the components. Now subtraction is going to combine the ideas from both addition and multiplication. So going back to these same two vectors, we're going to find V minus W. So I'm going to start out with the same idea as before. I'm going to graph V first. So V is at negative 2, 3. It's going to go right here. And W, we can kind of start with the idea of W, because what we're going to do is we're going to re-express this V minus W as V plus negative W. Now, typically, W would go over 3, down 1, just like it did before, right? So there's our original W. But this time, we want negative W, which based on what we did in the multiplication in our previous example, is we took W and we just flipped it over. So this time, this guy right here, that's that negative 3, positive 1 now. So we're just going to go left 1, 2, 3 units and up 1. So it's the same vector, but all we did was flip it over. And now, since we're still working in the framework of addition, we're going to go back to this idea of taking the end of, or the tail of V and connecting it to the end of W. And this vector right here is our V minus W. And if we want to check this with our component-wise subtraction that we did earlier, this is indeed that negative 4, or negative 5, 4 that we had earlier. So to kind of wrap this up, I want to start talking about the idea of the length of a vector and the idea of a unit vector. Because what this is going to do is allow us to break down a vector into its individual pieces of magnitude versus direction. So like we've been working with, vectors can be defined in terms of their components. So V equals that xy. And if we draw this on a graph, it looks something kind of like that. And the x component is horizontal like so. Y component is that vertical part. And notice that this horizontal and the vertical part form a right angle. So what this means then is this vector is forming the hypotenuse of a right triangle. And we know the sides of this particular right triangle. They're x and y. This means that we can use the Pythagorean theorem to figure out the length of this vector to be x squared plus y squared. So that gives us our definition. Length or magnitude of a vector V when we have its components x, y is given by, and the notation that we use for this is these two vertical bars surrounding our vector V. We just take the components of the vector, square them, and add them together. Quick example. Let's take v to be equal to 3, 4, and find its length. We just square each of those components, add them together, take the square root, and we're going to get 5 as the length of that vector. All right. We are now ready to talk about the idea of a unit vector, which kind of separates out the direction of a vector from its magnitude. So we define a unit vector, u, to be a vector such that it just has length 1. And we can actually turn any vector v that we want to into a unit vector. And I'll give you the formula for that. Specifically, what we're going to do is just divide it by its magnitude. So here's what that formula looks like. That u is going to be equal to 1 over the length of v times that vector v. Okay, so here's an example. We start with a vector 2, 1. We're going to find a unit vector with the same direction as v. So we want a u such that it's equal to 1 over the length of v times our original vector v. So we're going to have 1 over the length of v is given by the square root of the sum of its components squared. So it's going to be 1 squared plus 2 squared times the vector 2, 1. Simplifying that down, you get 2 over root 3, 1 over root 3. And this is our desired vector. It points in exactly the same direction as our vector v. The only difference is that it's been scaled or shortened so that it only has length 1. And we can actually check that just by looking at the length of that vector u. So 2 over root 3, square that, add to it 1 over root 3, square that. That's going to be equal to the square root of 3 over 3, which is just equal to 1. So our result does indeed only have length 1. So that's everything for this video. Going forward, we're going to work with a few more other vector operations and look at some other things that we can do with them. Until next time.